Rechtse, Dumelang. Good morning. Goeiemorgen. I am going to assume that you can hear me because it's easier for me that way. Welcome to yet another Q&A on the project. So I had a session yesterday as well. Actually, can some of you just do a thumbs up if you can hear me, please? I thank you, Mr. George Kayode. I had a session yesterday, and in that session, I did explain quite a few things that seem to be common problems on your computer systems design. So I want to repeat just a few things that I said that are important, which we kind of missed because I started recording late. So if you just bear with me for 1 second, I'm going to share my screen with you. And I'm working off 2 devices, so please be patient with me if I take a few seconds to share stuff. Okay, so I should be sharing my screen right now, and hopefully that'll pop up soon. Okay, so the first thing I wanted to say, just because many people are struggling with it, it's very important that you treat the components in your state machine as separate components. So for the transmitter, for example, you want to have the counter completely separate from the rest. So I just want to show you what I mean there. You have, where do I start? For your transmitter state machine, you will have a transmitter state machine, FSM, and obviously inside this FSM, inside there, is a flip-flop that remembers the state. There's output logic, which may be as simple as a simple wire, nothing fancy, and there's next state logic. And the next state logic, that's just simple, I'll tell you now, it's just a simple sum of products type solution that looks something like that. That's a horrible OR gate, but that's all there is to it. And you just have to figure out what that sum of products is. And on the output side, there's some logic as well. And just to be sure we're on the same page, what this transmitter drives is 3 things. It drives an output enable for the counter. Sorry, I'm lying. An output enable for the tri-state. It does a counter enable. And it also does a shift enable. So those are the 3 outputs you need to drive. Now, if you think about the state machine that we have, I've told you how to do the state machine. The state machine has an idle state, it has a transmit state, and it has it goes back to the idle state. And in this idle state, all 3 of those are going to be 0. In the transmitting stage or state, all 3 of those will be equal to 1. So really here you can say all outputs is equal to 1, and here you can say all outputs equal to 0. And the reason I'm doing it like this is just to show you we have state idle and state transmit. This one we're going to call state 0. This one we're going to call state 1. We only have 2 states, so we only have to enumerate for a single bit, which means that this flip-flop is only 1 bit, it's only 1 flip-flop, but it also means that this output here, the output logic, is literally the same as the state. So over here, you'll just have a wire that connects it. There's no logic. The logic is essentially just, it's equal to. So there's no AND gates or any OR gates or NOT gates. There's no silicon required. Right, so what I was about to say when I interrupted myself is you need to think about the fact that you have 3 independent components. So you've got the state machine that I've drawn there. Then you have a counter, and then you have a shift register. And you have to independently, let me rephrase. You have to control those using your state machine. So just as a quick revision, the way the shift register works is the shift register has a parallel input, and it has a shift input and a shift output. It can also have a parallel output, which you will use for the receiver, but not for the transmitter. So for the transmitter, I'm just going to draw the transmitter part real quick. For the transmitter, I said I have two states, idle and shifting or transmitting. And in the idle state, I'm going to program this thing to either load the values on each clock cycle, all four of them are clocked in, or if it's in the transmit state, it's going to shift stuff through from flip-flop to flip-flop. So on each clock edge, and let me draw those in real quick, there's a clock input here. And on each clock edge, it's either shifting through one position at a clock edge, or it's moving all 4 bits in at the same instance into the 4 flip-flops that I've connected here. That's how a shift register works. You control which one of those two it does by controlling something like a shift not load input. You can also invert that logic if you want it, but this makes it a bit simpler. So we're saying if that input is low, it's just going to load all this stuff in. So while it's idling, it's drawing in that parallel data, that 4 nibble or the 4 nibble bits. It's pulling into the flip-flops every single clock edge. And only when we transmit then does it stop loading and does it start shifting out. What I'm trying to say here is you have 3 separate components: the state machine, the shift register, and the counter. And for the counter, we have a control which will be something like count enable. You will see if you go into digital, there's a counter built into it. I just want to see where it is again. I think it's under memory components. I'll come to your questions in a second. Sorry, I just want to quickly go through this. It's under memory. There's something called counter, and that counter has an enable. It has a clock input, which obviously means it's going to start counting. It has an output of n bits. You decide n by right-clicking onto it. And those n bits a binary number. So that binary number is the thing that you have to then check to see if it reached the value that you want it to be. So what I told the class yesterday is, over here, just put in a logic gate, like an AND gate, for example. Maybe you want to add inverters here if you want, but that's not necessary in this case. And this output here, I've called something like count max, or count reached, or transmit count max reached, or something, what you want to call it. And the inputs into your state machine are really those. It's the current state, or present state, is the one input. The other input is, has it reached count max? And I'll show you why in a second. That is the input. And then the other input is start TX. So start TX will initiate the state machine. Then we have count max reached, and we have the present state, which also feeds into that input. And the way that it works is the idle state transitions over when we have start TX equal to 1. Actually do that, start TX equal to 1. And then this transition here, this one here, happens when the count max is reached. So count max is equal to 1. Right, so what you have to do, and it looks like this is what many people struggled with, you have to derive this logic and this logic, but we've already done that, so you don't have to worry about that now. We just said it's purely connected. You have to derive this next state logic from this diagram. So just to take it one step further, to be sure that we're on the same page, what that means, I've just drawn the whole thing here again. What that means is that you set up a truth table. And in this truth table, you have current state, you have start TX, and you have count max. Those are the 3 inputs, because that's the thing that causes the transitions to happen, and then also looking at the present state. And then you write down all the combinations. So in this case, I've written down the current state is 0, start TX is 0, then it needs to stay in state 0. It doesn't matter what count max is, because count max does not take it out of that state machine. For the state 0 and start TX is 1, again, it doesn't matter what count max is, because count max does not take it out of that state. You could have, yeah, sorry for interrupting myself. Then the next state is equal to 1. So if start TX is 1, then the next state is 1. If start TX is 0, the next state is 0, regardless of count max. Obviously, you could have split this up into 4 separate lines and indicated the 0 and the 1 and the 0 and 1 here. But what you have to do is do that for all the conditions. So I've shown you half the truth table now, but that truth table you need to convert into a Kano map with the count max input and the state input and the start TX input. You derive the logic and you put that logic in here. And like I said, that's just two AND gates and an OR gate. It's completely separate. For the receiver, it's a similar thing. For the receiver, I have to find three states. I have an idle state, I have a data receiving state, and I have a wait for the data ready to go high state. So this is basically waiting for a low on the receiver. As soon as it receives a low on the receiver, it goes into a data receiving state, and then can you show by show of hands just quickly if you can still see me, please? My PC's just crashed, so I'm on one of my devices. Or just say something. Okay, perfect, thank you. Hopefully you can still see what I'm showing as well. And then in this state here, it just stays for one clock cycle, stays high while that data ready is equal to 1. So this could be why you have that 1 clock cycle delay, the person who just asked the question. But essentially, for the receiver, your inputs are the serial line, which comes in, and then that count max. Those are the only two things that really causes transitions. So it's either going here, if state is equal to 0, and receive is 0, or it's going here from that state if state is equal to receiving and count max is 1, so it's received the total number of bits that I was expecting, and then it waits for 1 clock cycle and then transitions. There's nothing that drives this transition, it's just a clock cycle. So when there's a clock cycle, it goes into the next state. And then the outputs that are driven by this state machine, the way that I've designed this, well, let me just take one step back. I've obviously enumerated my states as 0, 0, 0, 1, and 1, 0. So the 1, 1 state does not exist. So in your truth table, there'll be a 1, 1 that's a no care or don't care. And the outputs. So the outputs, the way that I've designed this thing to work is, again, I have a state machine, then I have a shift register that receives into the serial, into the shift register. It's driven by the clock, but then the shift enable, or the clock enable, you can decide how you design it, is also controlled by my state machine. So the one output is shifter enable, the other output is clock enable. So the clock needs to start counting as soon as you enter this state, so that you have a count max, which will obviously again be the counter output. You check with an AND gate, and then this goes high when you received all the bits and the count has been reached. And now I'm gonna shut up and have you talk. While I'm resetting my computer, you're just gonna have to, can you raise your hands? I don't know if you want to try. Yeah, there's a hand raised. Miss Ackerman, oh, you're on the second session as well. Please go ahead.
Hi, sir. My question posted on the Teams channel, but it hasn't been answered yet, which is fine. So I just wanted to ask it here. All of my tests passed, but I do want to double check something, because when I went to go check the tests, I saw that the sort of bit transmissions weren't very overlapping. Anyway, sorry. The main question is it right that between two consecutive sort of sections of shifting bits, if the start TX stays on, is there going to be one clock cycle where it has to transmit and the
Sorry, Ms. Ackerman, I'm just going to mute everybody. I'm just muting everybody. Somebody's got their stuff turned on. Can you unmute yourself again and just ask again, please? Go ahead.
So is it right that if you've got start TX on, so that you've got like 2 cycles of transmitting all of the bits in the register,
yeah,
is there one clock cycle in between the 2 transmissions where it's not transmitting and the serial line is just high?
Yeah, we seem to have some feedback. I think I hear you saying, and I remember seeing that question. Let me just quickly think about it. So the way that I've designed mine, and I guess it's up to discussion whether my method is the best method to do it. I've designed it such that after it's transmitted the stop bit, it goes back into the idle state, and only then does it go back into the transmission state when the transmit is high. So there will be a clock cycle in between the two nibbles. Is that what you mean?
Will you just repeat like the last little bit that you said, the last few words?
So there will be a clock cycle in between the two transmissions, in between, because it goes back into the idle state, and only then does it start transmitting again. But the transmission, when you set the start TX high, the start bit is immediately sent. So, sorry, I'm just thinking, give me a second. So it loads it in the idle state, goes into that state. Yeah, there should be a clock cycle delay between them.
Okay, yes, that's also what I was thinking, because it goes to the idle state for one clock cycle.
Yes, but yeah, exactly, yes. And then on the next clock cycle, the start bit will be transmitted again.
Okay, thank you, sir.
Sure, but all your tests pass, right?
Yes, they do.
There are people with much bigger issues.
Okay.
So well done, Ms. Ackerman. Okay, yes, okay. Mr. George Coyote. You need to unmute yourself. Okay, I'm going to give you 5 seconds and then I'll move on to the next. Oh, there we go. Yes, okay. What's your question? Yes.
Okay, good morning. I tried these circuits and I don't know what seems to be wrong. Can I show you my screen?
You can try, yes.
Thank you. Can you see my screen?
Yes.
Okay. Now I tried running these and it's worked, but I didn't pass the transmitter test and I literally don't know what seems to be wrong.
But Mr. George Coyote, you need to be a bit clearer. I mean, okay. You're just saying it doesn't work. You don't know what's going on. What are the symptoms? If you go to the doctor and you tell him I'm not well, he's going to ask you what exactly do you mean?
So okay, anytime I run this test and it shows for the transmitter test, I'm just going to show you just now. Just a moment.
Can you do me a favor while that is running?
Yes.
Just go onto your circuit. Do you have access? Okay. Just go onto your circuit, close this, and go to the tests. Scroll up to the test. No, the test. The green buttons on the. There we go. Just for a moment, just undo that. Just right-click the receiver test.
Edit.
No. Close this. The receiver test. Right-click it.
Okay. This.
Yes, and not enabled, so disable it, just to save you a bit of time. There we go, and the next one as well. Okay, go ahead. So just run it again, but okay, yeah, sure, run it again. Yeah, okay, and run tests, cool. So while this is running, I just want you to consider that you're just running a test. You're not, have you tried this manually? So just playing it, and okay, and does it work then?
No.
Okay, no. But then you should really start there, because this test is not something that's supposed to help you debug. It's there to test whether the circuit works. So show me what is wrong.
Okay. Now this is my shift register here, and so I built a counter here with this is my counter, and this is my flip flop, and I built a parity bit here.
Okay.
Then I noticed my my bits were shifting.
Did you say your bits are not shifting?
I noticed they were shifting before they weren't.
Yes.
But now they were shifting.
So Mr. George Coyote, where's your state machine?
So this is my state machine. I used the counter and
But where's your so you know what I just showed you about the truth table, the truth table that leads to a next state logic that goes into a flip-flop. Where is your next state logic?
I just show you just now. I'm just going to show you just now. So I removed it once it wasn't working. I was just going to show you just now. Can you see my screen?
Yes.
So this was my second trial where I used my next state logic.
Yes.
This is my next state logic here.
Okay. So this is good. This is very similar to what somebody did yesterday. So this seems to be a common problem. So I want you to,
yes,
you know, I need you to take a step back.
Okay.
This next state logic,
yes,
looks right. I'm not looking at it in a lot of detail, but it looks fairly. Oh no, bugger. Okay. Let me just take a step. I'm going to go through this process. So everybody just bear with me because I think it's useful to many people if we debug this. So Mr. George Coyote,
yes, sir.
I'm just going to call you Praise because it's much shorter.
Yes.
Could you delete the line that goes, or first of all, explain to me the line that goes from that inverter at the top to the driver, to the buffer? What does that do?
Okay, this is to select. Let me check my notes first. This is for my. This is for my counter. I think so. I'm trying to check my circuit just now.
Okay, I'm going to give you a second or two to think, and then I'm going to tell you. I'm telling you. Okay, so tell me. I'm going to ask. I'm sorry. This may be painful, but like I say, knowledge gain is painful. So stick with me. This is not to embarrass you. It's to try to show everybody. Okay.
Okay.
The buffer that you have on the right. Just point to your output enable, the output enable line on the tri-state buffer.
Tri-state buffer.
Yes. So you don't have to zoom in. Just like this. Just hover above the output enable. Do you agree that this output enable line is an input into the tri-state buffer?
Yes.
Okay. Just go to the inverter that's connected to that. Do you agree that that point there is an input?
Yes.
To the inverter. Okay. So do you agree that you're driving two inputs against each other?
Oh. Okay.
Okay, so that means that is not doing anything. That's essentially a floating line. That line is dead. Can I ask you to delete that line real quick, please? Okay, now I want you, delete it, perfect. Now I want you to just, maybe just for the time being, shift the counter out. So take the counter, Control X, everything related to the counter and move it elsewhere. You missed the counter. That's fine. You can take the rest later. There we go. Okay. Now we have the counter separately there. Up to what do you want to count? What's the number you want to count up to?
6.
So right click your counter, please. I just want to see something. You have one data bit. So this counter counts 0, 1, 0, 1. How many bits do you need to count up to 6?
3 bits.
Yes, exactly. So make that 3. So this will now count 0, 0, 0, 0, 0, 1, 0, 0, is a 0, 1, 0, 0, 1, 1. This will count in binary in 3 bits now. Okay, Mr. George Coyote, also known as Praise. How do you check whether 6 has been reached?
Try and AND gates.
Exactly. So please do that. Okay. It's under logic. How many bits do you need to check?
2 bits.
Okay, which 2?
I'm just going to write this down. 60.
Six is 110.
Yeah, 110.
Okay, so now we have an issue. That output from the counter is 3 bits, but the AND gate needs to check 2 bits. So the stuff that comes out of the counter is a bus. It's called a bus because it contains multiple bits. So there's a splitter. If you go to components, you can add a splitter. It's under wires. Splitter merger, there we go. Put that there. How many bits on the left? 3. How many on the right? 2. So, I mean, 2 separate ones or 3 separate ones. So right click that splitter.
on the input side, you've got 3. On the output side, you want 1, 1, 1. So it's 1, 1, 1. Those are the 3 outputs. There we go. So now you can connect that data bus of 3 bits. And now you just need to select which 2 bits to check against with the AND gate. What I'm showing you, I'm painstakingly going through this process with you, is breaking up a bigger problem into smaller chunks. A big part of engineering, and you should have been taught this in computer programming, is divide and conquer. Take up a bigger problem, breaking it up into chunks. You first want the counter to work before you look at something else, or you first want the state machine to work before you look at something else. You want to break it up into subcomponents. Okay, what is still needed here? So this is gonna clear clock. So your clock enable.
Yes.
No, stop, don't do that. You've got a clock enable that you've connected to 5 volts. This
Yes.
means your counter will keep on counting all the time. Is that what you want?
No.
When do you want it to count?
To 5. To 6, sorry.
Yes, but I mean, so do you want it to count all the time? Do you want to go 0, 1, 2, 3, 4, 5, 6? When do you want it to start counting?
Sorry, come again.
When do you want it to start counting? When do you want to initiate the counting?
When the start bit starts TX is 0.
Exactly. And what is the thing that remembers that state of yours?
The flip flop.
Yeah, exactly. Where's your flip flop? Now, while you do this, I want to just make, that's, wait. Oh. Mr. George Kayole, I'm slowly starting to get a bit hot under the collar. Just show me what you think is a flip-flop again.
Okay. Sorry, this.
Yes. I wanted to say in your other circuit, you also use this. Okay, so this is now the thing that's going to remember the state. Okay. So you want that thing to give you an output, telling you what the state is, and whatever comes out there at Q is the thing that's going to drive the enable of the clock. So rather than having to move all the components about, just make a tunnel. I'm just going to give you a few more seconds of attention, then I'll move on to someone else. But put in a tunnel. It's under wires, I think, or IO, I can't remember. There we go. Okay, and connect that onto Q, and then you call it, right-click on the tunnel, and call it counter enable or CNTEN or something. You can really call it whatever you want. Rather not use spaces. Many of the programs in engineering and computer programming don't like spaces. Back when I was a child, we weren't allowed to use spaces, even in file names. So you've connected it to not Q. You wanted to connect it to Q. Do you agree?
Yes. I think I connected it to Q.
The uncomfortable silence is to help you realize that you're wrong.
No. Okay. Just...
Okay. There we go. Thank you. Okay, so now we're connected to Q. So now you've got the output logic that you essentially have is a piece of wire saying start counting. So now you need to connect that tunnel to the other part as well. Just click on the tunnel and copy it over to your counter enable. So now your counter will start counting when your state machine says state 1. Do you agree?
Yes.
Okay, this is good. You need to do the same with your tri-state buffer and the same with your shift register. They also have to be enabled, but you're not going to do that now. I'm just telling you. They also have to be enabled when the state is 1. What is missing in your state machine? A state machine is made up of output logic, a state rememberer, a memory thing, and then a next state logic. What is missing?
Okay. I have. Okay.
Yes, that's your next state logic. So that next state logic there, which is the moment for some reason is driving into the multiplexer select line, you need to take this out. So just Control X that whole sum of products piece of logic and put it, Control Exit, and make it feed into your flip-flop.
This.
Yes, exactly. Into, where does it go? Into D, exactly. So now that tells the flip-flop, when there's a clock edge, go to this state that I'm telling you to go to. So just So let's just think about this quickly. So the start X goes into the AND gate and then knot it with something. So somewhere in your truth table, what is that thing that's knotted? That's inverted.
Yeah, the clock.
No?
Sorry, the counter.
No. So I don't know how you did your state machine, but basically the inputs into your next state logic is start TX, counter max reached, and present state. And that present state you've currently connected and you've called it output enable. So maybe just zoom into that, into the output of your flip-flop. I'm just going to try to make this as clear as possible. Add another line there.
Yeah.
Yes. Make something else connected to it and call that present state. Also give it a tunnel. Or TX state. Or TXS or S underscore TX. That's actually the nicest one. S underscore TX. S for sugar, S underscore TX. Okay, cool. So that is no. There we go. No. Okay, so that tells you what is the present state. So that is the thing that needs to feed into this next state logic of yours.
Yeah.
Yes. So you need to go to your truth table and determine what the logic is. But just thinking about this, if start TX is 1 and present state is 0, you want this thing to go into state 1.
Yes.
So what you've done is right now. I don't know if it was accidentally or not. Now you need to do the same with the bottom one. But I don't want you to take guesses and just connect things up and try it out. I want you to go to the truth table and see what the next state logic is for the case when state is 1 and count max is equal to 1. Then it's supposed to transition into state 0.
State 0.
Yes, so you have to stay in state 1. The other way of looking at it is stay in state 1 if count max is equal to 0 and state is equal to 1.
Yeah.
Right? So you just need to populate the rest of that AND gate. So now you've got the counter and the next state logic and the flip-flop and the output logic right. The only thing that's still missing is the shift register. And the shift register, you just have to control the shifter and that shift enable line, which is basically the input into the multiplexer, you have to control from the output of the flip-flop. And then you're done. So I don't want, yeah, exactly, because that drives that controls the shift register. So same as you have there, maybe just zoom in a bit. Just click on count enable. Or,
Count enable. Which one? For the
just go to the output of the flip-flop. So
okay.
You need there to add another line called shift enable and another line called tri-state enable or something like that. So you know you've got.
Yeah.
Hang on. Just listen for a second. You know you've got count enable there.
Yes.
You also need a similar thing there connected to exactly the same line that you call tri-state output enable and another thing that you call shift enable or shifter enable or shift not load. And then when it's in the state, it's either shifting or it's loading. So you need to just add that and then you should be done. So I'm going to let you go because there are other people that need help as well. Okay.
Thank you so much.
You're welcome. Please stop sharing. Let's see who's next. I think it may be, who was next? I think it's Zoitmir. Miss, please go ahead. Ms. Zoitmir.
Sorry.
There we go.
Yeah,
yes,
sorry, I struggled to unmute myself. Hello, sir. I'm
Hello.
struggling with to get my transmitter right, and the only thing that I'm not quite, I don't think I understand it, is the inputs to my shift register. So there's a serial and load, and also another input. So I don't know if I know what should go in there.
Okay. I'm gonna can I share my screen and show you?
Yeah,
again?
that would be nice.
Okay. But I would strongly recommend, Ms. Zoitmir, that you have a look at the lecture. I think it's called combinational logic, where we do shift registers. It's quite important that you understand this. This was actually in the exam as well. But the way that a shift register works, I'll go into a bit of detail here, but then I want to point you to the lecture. If somebody can check up which lecture it is, please do so. But your shift, I'm just going to do a one flip-flop shift register. this is, can you see my screen, by the way? Sorry, I'm just assuming you can.
Yeah.
Okay, cool. This is a 1-bit shift register. What we're saying is, when this receives a clock, it's going to take this and move it across here. Stop me at any time if I say something you don't understand, okay?
Yeah.
It's going to move it over there. If we receive a clock, it's going to move it over here, and actually I'm just going to expand this a bit. Sorry, I'm thinking on the fly, so I may be changing my mind real quick when I explain it. And I'm trying to explain it in as simple as possible terms. Right, when we get a clock edge here, what will happen is whatever is present at this point will be copied and put onto this point, and it will be remembered, right? That clock edge is going to clock that value through onto here, but because it's synchronous, it's also going to take this value and put it here. So as soon as the clock strikes, two things happen. This thing is copied here, and then also whatever was here is copied here, which has the effect of shifting. Do you agree?
Yes, sir.
Okay.
Yeah, I understand this. It's more like at the beginning of my shift register.
Yes.
Like I did the lectures, but I think I'm just.
Are you on the transmitter side or the receiver side?
Transceiver.
No,
Transmitter. Sorry.
Cool. No worries. Yes. So what we then do is we add a multiplexer, and
Okay.
this multiplexer is just saying, rather than always shifting, I want to sometimes be loading the shift register of mine in one go, all the parallel inputs. So we're adding a multiplexer here with a select line that's common across all the flip-flops. And it says, either I'm shifting, so either I'm taking all these values as it was just now. Just give me a second to think real quick. When that is low, I want it to load. So I want this. Okay, there we go. Yes. So we're saying if this value is 1, and that's the one input of the multiplexer, it's just going to act like a normal shift register. All right. So I have an input here. This I'm going to call serial input, and I have another input here. So in terms of the multiplexer, we're connecting it like this, which means if this input is 1, it's going to have that shift effect. Do you agree?
Yeah.
Okay, cool. Now what we add is we add 2 extra lines. I'm just going to do this in a different color. We're adding this here and this here, and we're calling this, let's call this D0, and this we call D1. If this line is high, it's essentially just a shift register. It's just moving things across. If it's low, it's actually taking these values and latching them into the queue. So either it's shifting each one of the flip-flops values on one position, or it's taking these at one instance, one clock edge, taking all of them into their respective flip-flops. So the inputs that you're talking about that you're unsure of it's this one. It's called shift, not load. Oh, I almost spelled it wrong. Shift, not load, which is the one input. You've got the serial input, and then you've got the clock input. Do you agree with all of this?
Yeah. That
So
is basically what I'm not sure about.
Right. So everything that I've said now makes sense because there's only one more step. Okay.
Yeah.
Now there's one more step, and you can go and look at the lectures for this, but there's one more step where we say, do we want this thing to be enabled or not? But we don't really use that. We're actually just going to use this as if it's an enable line. So we're saying, while we're in state 0, just continue loading because we want to be ready to start shifting when the time comes. So for each clock edge, we're loading stuff in this path here. We're loading it in. And then as soon as the state changes, we change the state of this line with our state machine. This is what Mr. George Coyote still had to do. We're changing this to a 1, which means whatever was loaded in the previous cycle, we're now going to start shifting it through. Does that answer your question? No.
Yeah, kind of, but I'm still not sure what to do, but that helps a bit.
But which inputs? But I'm really
Yeah.
troubled by this. Help me, Mazet. Like, you know, what did you
Okay.
not get yet?
So I understand the shift register, like how it works. I'm just not sure what to put into my shift register to make it work, because it's not working at the moment.
So you need to connect these lines to the data tunnels that I've given
Yeah,
you. That
I
you
have-
make you understand.
Yeah, that I
This
have.
serial input, you don't have to connect to anything.
Okay, can it just be open?
Yes, because you're going to stop shifting
Okay.
before this thing reaches the end.
Oh, okay.
This you
makes-
connect to clock. This you connect to the output of your state machine.
Okay,
So
cool.
the state machine controls this. Does that answer your question?
Yeah, that answers my question. Thank you very much,
wow.
sir.
Okay, cool. We could have gotten there much quicker. Sorry. Okay, cool. So I'm
Sorry.
going to move on to the next person, okay?
Yes.
Perfect. Next in line is Mr. Shenny.
Hello, sir. Can you hear me?
Yes, I can. How are you doing?
I'm good. Sir, I think there's two signals I don't really understand. I think it's start TX and data ready. So, I'm just gonna share my screen with you.
Go ahead. Start TX and what?
Data ready.
Oh, okay.
Yeah.
Actually, can I? So you can share your screen in a second. I just want to explain to you what it does. Okay.
Okay.
And then you can show me. So there's the transmitter. There's the receiver. There's one line in between. You can see my screen, yes? Yes, you can.
Yes.
Start TX tells this thing, push all the bits through. So it goes from low to high, and then this thing starts to shift the bits 1, 1, 1, 1, 1 onto the line. This here looks at serial. Serial is this line's name here. And it says, okay, I'm receiving stuff. As soon as it's 0, it goes into receiving mode. It then shifts in, and it shifts until it's received the stop bit. And then as soon as it's received the stop bit, it makes data ready high for one sample, so that the receiving microcontroller or whatever is receiving, whatever is using this receiver, knows that the data is ready, it's been received. Okay, now go ahead with your question.
Oh, okay. Okay. Yeah, thanks. The data ready, I didn't understand it properly, but now it makes a lot more sense. I'm gonna share my screen.
Do you still want to?
For the transmitter side, yes, for the start TX.
Okay.
Okay.
While you do that, I'm just going to make a comment. So you can do that. Go ahead. That data ready, you will see, is the thing that latches the display on the 7 segment. So that's the thing that causes the flip flop on the display to show the value. So as soon as this data ready goes high, it displays whatever was on that data port. Okay, go ahead, Mr. Shenny.
Can you see my screen?
Not yet. Okay, it's coming. Yes, I can.
Okay, so this is my transmitter test, and so most of my errors happen like the next clock cycle after start TX is high. So here's one. This is maybe this is a bad example, but yeah, this is the next clock cycle. So it's after TX is high for the first clock cycle. The second one, there's an error. And then also when start TX goes low, the next clock cycle has an error.
Can you show me your circuit? I just want to have a look there.
Okay. Should I explain what I was trying to do?
No, just give me a second to look at it. It makes me happy. So the only thing that seems dodgy here, that's actually efficient TX. That enables that enables this enables the counter. And you stop at 6. That says count and count. So the errors that you just showed me, is that on the serial line? Is that on the transmitter side?
Yes, it's on the transmitter side. It's in the serial line.
Where's your start bit?
My start bit is here.
There's the error. There's the problem. Okay. So you are the first bit that you're supposed to transmit is the start bit, but for some reason you're transmitting start TX. That's what's causing the problem.
So wait, which one is the start bit then?
The start bit is 0. It's always 0. So just go back to your shift register, which in your case is misses an F. Just go into the start TX. Zoom in, zoom in, zoom in. There, that thing there, you can just make it ground because you want the start bit to always be 0. So you don't want to send start TX. You want to send the start bit, which is always 0. It's regardless of what the inputs are, regardless of anything. That must be ground.
That makes a lot more sense, actually.
I'm glad. Mr. Sheni, I'm going to drop you. Next in line is Miss Malatsi. Miss Malatsi Utsohilejang. You need to unmute yourself.
Good morning, sir.
Good morning.
I wanted to know if you could explain the receiver again, because in the last Q&A, you started recording late, and today you only briefly went through it.
Just say again, in the last, I did what?
The last Q&A.
Yes.
You started recording late, so the explanation is not there in that video.
Oh, you missed it. Yeah. Let me do that again. Okay. So for the receiver, where do I go? My life is one big note. There we go. Okay. So for the receiver, I have an idle state. I have a data receiving state. So I've received the low on the RX, and then I go into data receiving, and then I have a state in which I make that data ready high that Mr. Sheni was just referring to. Do you understand the state machine, Ms. Malatsi?
No. Are you sharing a screen?
Ha! I'm supposed to. I'm kind of glad I didn't, because I accidentally showed all the truth tables and the Ghana map. So let me quickly start sharing screen. Thank goodness. Sharing screen. Tell me when you can see my screen, please, Ms. Malatsi.
Yes, I can see your screen.
Okay, excellent. So let's just take a step back quickly and think about how it works. It works in the following way. The receiver just sits there and does nothing until it gets a low on the serial input. Then it receives bits. It receives a start bit, it receives 4 data bits, and it receives a parity bit and a stop bit. So it's receiving 7 bits. As soon as it's received 7 bits, and with receive, I literally just mean it reads the line. It reads the line for 7 clock cycles, or clock edges, I should say. After it's read the line for 7 clock edges, it goes into a state where it just makes data ready high for 1 clock cycle to tell the display I've received a nibble. Then it goes back into waiting. Does all of that make sense, what I've just said?
Yes, it does.
Excellent, thank you. Thank you for the question, by the way. Okay, so the way that I have thought about this, I've said, right, it's idling, it's waiting, so I need an idle state. Then as soon as the receiver goes low, I want it to go into a data receiving state. As soon as it's received the right amount of data, and this is what I'm trying to denote here, I want it to go into a waiting state for 1 clock cycle, where it's just going to allow the processor to say, hey, there's a bit here, and make data ready high. So it's saying to the display, I've received data, I'm making data ready high for 1 bit, and then I'm moving on back to idle. So I've got 3 states: idle, receive, data ready high. I'm giving those states numbers, 0, 0, 0, 1, and 1, 0. Because I have 3 states, I need at least 2 bits to represent them. I don't use the state 1, 1. It's a not used state. Then I have to ask myself, okay, what is the thing that causes the transitions? Obviously, this is serial is low. So that's my one input into the state machine. RX is low, but in your case, you call it serial. So let me just fix this so there's no confusion. Serial and serial. Now, as soon as serial is low, that transition happens. The other transition that happens is here, is when count is high. So I need to make something that counts up to a certain number, and then when it reaches that count, it must go into the next state. So this is another input into my system, count. Same as in the transmitter, it's like count max. It's something that's going to say I've reached that max state. Then this transition here just happens. Nothing causes it. It's just an automatic transition. it means it's going to be for one clock cycle. So the thing that causes this transition is a clock cycle. In other words, it just happens. Right. Are you still with me, Ms. Malatsi?
Yes, sir.
Okay, I'm just going to mute Mr. Shenny because he's making noises. Okay, then what you need to do is you need to ask yourself, what are the outputs and what are their values in each one of the states? So the outputs are, I have a counter which needs to count the number of bits. So I need to control that counter. I need it to start counting when it's in this state. So one of my outputs will be counter enable, which is what I'm trying to indicate here. I've actually designed it slightly differently. So let me just think about whether I should explain the most common way of doing it or my way. That's fine. Yeah, so here I have one output called count enable. So this count enable will cause the counter to count. Then I have to control something else. I have to control the shift register. I only want the shift register to shift when I'm in this receiving state. Hopefully you agree with that. So one of my outputs will be shift register enable. Then you can obviously have them connected if you want it. Then I have another output, and this output I have connected to say data ready. So what you should quickly realize is in the idle state, my shifter should not be shifting, so shift enabler is low. The counter should not be counting, so count enabler is low. And the data ready is also low because I haven't received data. In this state, my shifter must be enabled, my counter must be enabled, but my data is not yet ready, so data ready is equal to 0. In this state here, I've got data ready is equal to 1, and I also have to enable my counter, and I have to enable the shift register. So you may derive from what I've shown you is I've kind of cheated here, and I've just put one control in to control the clock, but it doesn't matter how you do it. You have 3 outputs, and there's a value for each one of the outputs in each one of the states. Still with me, Ms. Malatsi?
Yes, sir.
Brilliant. So now you need to draw up a truth table. So let me show you the first 2 lines of the truth table. I've got present state or current state, which is my S1 and S0, I've called it. I've got the receiver line, which I called serial in the circuit, and I've got that count max thing. So let's just move back to the count max thing quickly. For the count max, you're going to have to use a counter, and in the same way as the transmitter, you're going to have to check whether the max value has been reached in that with an AND gate, right? So this is count max, or just what I've called here count, right? So it doesn't, so if I'm in the 0 state, I'll show you 2 lines here. If I'm in the 0 state, it really does not matter what the value of count is because count has no bearing. It doesn't affect going from the idle state. So that's a don't care condition. If Rx is 0, so if the serial line is 0, I need to make the transition. So if Rx is 0, the next state must be state 1. If Rx is 1, then I just stay in the present state. If you now do this for all the input conditions, so you write down all the possible values here, then you end up with a truth table, which you need to convert into a Kano map. I'm hoping that you're comfortable converting into a Kano map. Once it's in a Kano map, you just derive the logic for the logic that relates to the next state and the input conditions. And that's basically what you put in here. So you've got those 2 bits, they fed back here. There we go. So you've got 4 inputs. That's your receiving line, the serial line, count max, current state bit 1, current state bit 0, and the logic here you get directly from the Kano map. I think that's all I'm comfortable saying at this point, Ms. Malatsi. Is that okay?
Yes, sir. Thank you.
You are more than welcome. Hey, there's no more questions. Let me just check if there's anything in the text chat quickly. Oh, Mr. Shenny, you're back. Let's just give someone else a chance as well real quick. I'll be with you in a second. Should be lecture 14. Thanks, Ms. Ackerman. Thank you. That was Ms. Wilson. Hey, Ms. Wilson, did you get your circuit to work? I'm going to assume yes. Okay, any other questions? Okay, Mr. Shenny, looks like no one else wants the chance. If you want to, you can go ahead.
Hi, sir. I still have the same problem. I think it's a clock cycle problem now, though. Can I share my screen again?
Okay. But just mind, I'm not going to bring you all the way, okay?
Oh, okay.
But you can show me. I'll decide.
I think right now the problem is here now. I think I might have an extra flip-flop. So what I think is wrong is that if there's a 0 here and needs to go from this line all the way to the serial line, then it needs to go with this clock. It has to be first clocked into this flip-flop and then it has to be clocked into the serial line.
Mr. Shenny, I have a wild imagination, but I can't see your screen.
Oh, can you see my screen now?
No. Can anybody else see your screen?
Oh, wow.
Maybe the problem is on my side. I don't know. I just see big black. There we go. Yes, it's shown now. Go for it.
Okay. I think my problem is here. I think I might have an extra flip-flop because for this 0 to go from here to the serial line.
Oh, okay, gotcha.
Yeah.
Just zoom out. Zoom out. Sorry, I'm going to try to save time. Just zoom out. I just want to see where this output goes.
Oh, it goes to the serial line.
Why do you have that pull-down resistor there?
It's probably because there was a ground there, so I thought that the ground still kind of needed to be there or something.
Oh, okay. But the yeah, so the flip-flop will drive that. Just looking 0, 0 max. FSMTX, select 0 and then output. And your state machine drives directly into Mr. Shenny, from just quickly looking at it, there shouldn't be a problem. This looks fine. Just go to the right a bit. And I just want to see your state
to the
machine.
Right?
Sorry, the other right. Yeah, there we go. I don't have the time to go into too much detail, but from what I see here, this should be fine. Why do you say it doesn't work?
Oh, okay. I think because my problem is like immediately after the start signal gets sent. So I think I'm like a clock cycle behind. So I think this 0 goes once in here, and then it needs another clock cycle for it to go onto the serial line.
Oh,
and
no, it shouldn't. No, listen, with each clock cycle, while it's not shifting, that will be clocked into the flip-flop. So the flip-flop should have that 0 there all the time. And when you finally start shifting out, that 0 should immediately be there. Why do you say it's not working? So I know what you think is wrong, but why do you say it's not working? What do you see that makes you think that it's not working?
Okay. So all my flip-flops are limited by this.
I see it. You've got an AND gate there, which controls the clock.
Yes.
So tell me, Mr. Shenny, I'm going to ask this in a pretty facetious way, so please bear with me. I'm pretty tired at this point of the project, as most of you will be as well. What's going to happen when your state machine is in state 0? Is it ever going to load?
I think so, because if it's in state 0, it's also connected to this. So when it's in state 0, it's going to use the multiplexes, which all have.
So what does a flip-flop need to clock something through? The answer is in that question.
I'm guessing it just needs a normal clock.
Exactly. So what are you doing with the clock? You're hiding the clock while your state machine is in state 0. Do you see that? That AND gate is hiding.
That's unnecessary then.
Yes, exactly. You're hiding the clock from your flip-flops while you're in a idle state. Do you understand why you've just done what you've done? I don't want you to just do what I'm telling you. I want you to learn from the experience.
Yeah, I did. What I was trying to do is I was trying to create like a clock enable so that my flip-flops would only do would only start shifting when FSM was there. But I see that the multiplexers do that already.
Right. So, okay. Listen, I need to grab something here. Just give me 1 second, okay? I'll be with you guys in 1 second. Sorry. Hey, this is amazing. Dankie. Dankie proses. Dit is amazing. Baie dankie. Waardeer dit baie. Ek's in klas, ja. Yes. Baie dankie. Good gaan. Okay, sorry, but Mr. Shenny, I'm going to assume that you know what's going on now.
I think so, sir.
Okay, brilliant. I saw another hand go up, before I take that question, can you just show by means of thumbs up whether you've learned something in this hour, please? Just make it worth my while. Okay, cool. Okay, a few. Mr. Hill, you'll be the last person I can help, then I have to run to a meeting.
Okay, sorry to bother. Can you hear me?
I can.
Okay, cool.
And you're not
perfect.
bothering. I'm here to help you. Go ahead.
Okay, thank you so much. I'm just quickly gonna share my screen. So far, I figured out how to do most of the project.
Just tell me when you believe your screen sharing.
Okay, there we go.
There we go. It's coming. Yes.
Okay, so far everything worked right. So if I tested, now send data through. I get the data on the other side, which is nice. But when I run the test,
I'm going to guess what's wrong before we look at it. I think
okay.
you used start TX in your receiver side. Do you think that's possible?
Let's quickly check.
Because it will work if you abuse start TX on the receiver side and tell the receiver when to start looking for data.
Yeah. I didn't use start TX for the receiver side.
You did not.
I used the serial line and the state to put the clock on, or to make sure that it's like clocks at the right moment.
Okay. So the other thing that could be wrong. Sorry, I've got little time, so I'm going to interrupt you. Beg your pardon. Just zoom into the block that you were not supposed to touch. Somebody's touched something inside there.
Yeah. So I put
yes.
this.
That's very nice of you to do for debugging. Okay, so that might have caused something. Just go into your serial line and just want to see if you've changed the name of the serial line. There we go. That's the issue. Have you? Just zoom into that little tunnel just to the right of the pull-up. No, you've not changed that name. It shouldn't be the problem. Zoom out, please. What is this clock that you're using? Are you using your own clock?
Yeah. But I figured out that all the clocks are synced.
Not necessarily. What do you set that frequency to?
1. So
yeah, no, I think that may be the issue, because I'm physically driving clock with the tests. So you've decided you're on your own clock, which means you're on your own. But I'm sorry, Mr. I forgot your name now. Mr. Hill. I have a meeting that's starting, so I'm going to have to run. But I think that's probably what's causing it. If you find that the test works when you run it manually, and it doesn't work when you run the test, it's either because you've changed the signal name, or you've mucked about in the no-go zone, or you've used the clock like you've done now, your own clock, which is just going to mess it up. Okay, I've got to run. I've got another meeting. Is it going better now? Did it work?
Yeah. I think it did. Thank you so much for your time.
You are more than welcome. Okay, guys. Hope that helped. Good luck with the submission.